Another common op-amp circuit is the non-inverting amplifier. And the non-inverting amplifier looks very similar to the inverting amplifier, with the exception of this. In the non-inverting amplifier configuration, the input resistor is tied to ground, or to the reference voltage of the circuit, and the feedback resistor comes from the output of the op-amp back to the inverting input terminal. Now, the input voltage is supplied to the non-inverting input terminal. If you'll recall, in the previous circuit that we looked at, which was the inverting amplifier, the voltage being supplied was provided here, and the non-inverting terminal was referenced to ground. So we're going to have a slightly different behavior due to this new, slightly different configuration. And we can elucidate that behavior by looking at the ideal op-amp model, which I've drawn here. Okay, so from the ideal op-amp model now, assuming that we have a zero input resistance, an infinite input resistance and zero output resistance, and that we can model the op-amp by this dependent voltage source here, we can establish the relationships that tell us how the output voltage is going to be related to the input voltage. Okay, so the first thing that we notice is we know that the voltage at the non-inverting input terminal is the same as the input voltage. So Vn is the same as the voltage at the non-inverting input terminal. We also know that the output voltage is going to be the same as the voltage provided by this dependent voltage supply. So Vout is going to be equal to some large gain factor A times the quantity of V plus minus V minus. But we know that the voltage at the non-inverting input terminal is Vn. So that's going to be the same as a large gain factor times Vn minus the voltage at the inverting input terminal. Okay, to determine the voltage at the inverting input terminal, we need to apply Kirchoff's current law. Okay, and we have two possible paths for the current to go, and we can write those in terms of node voltage equations. So from Kirchoff's law and from Ohm's law, we know that the current through this path, through the input resistor, is going to be given by the voltage at the inverting input terminal minus 0, because we're assuming this is our reference node right here, divided by Ri. Alright, that gives us the current through that path. And the current through the feedback resistor path is going to be the voltage at the inverting input terminal minus the output voltage, Vout, divided by Rf, and by Kirchoff's current law, that has to sum to 0. Okay, so my goal here is to relate the output voltage to the input voltage, and the way that I'm going to do that is to use this equation right here. Alright, I'm going to rearrange this, and if I do some rearranging, first I'm going to divide by the large gain factor A, and I arrive at Vout over A is equal to Vn minus or the voltage at the inverting input terminal, which allows me to solve for the voltage at the inverting input terminal as being V minus is equal to Vn minus Vout over A. Okay, so now I'm going to take that and substitute that into this relationship right here. And when I do that, I will wind up with Vn over Ri minus Vout over Ri times that large gain factor A. So that takes care of this term right here. All right, plus Vn over Rf minus Vout over Rf times the large gain factor A, and that takes care of this term right here. And I still have to worry about the Vout term right here, so that will be minus Vout over Rf equals 0. Alright, and I'll cancel this here. Okay, once I've done that, sorry about that. Okay, once I've done that, what I can do is rearrange and group some terms. And what I want to do is I want to get all of my output terms and my input terms on the same side of the equation. So I'll do Vn multiplied by the quantity R 1 over Ri plus 1 over Rf on the left-hand side, and on the right-hand side I'll bring all of these terms over that are related to the output voltage. So V out over 1 over Ria plus 1 over Rf times A. Oops. Sorry, I didn't mean to do that. And the other output term is plus 1 over Rf. Alright, so it's going to be multiplied by that quantity there. Alright, and now I can use the trick where we're assuming that the gain is nearly infinite, and as the gain approaches infinity, these terms right here are going to approach 0 and become negligible. Alright, so we're left with Vn multiplied by 1 over Ri plus 1 over Rf is equal to V out, and the only other term here is the Rf term, so I'll just go ahead and put that over Rf, right? And if I want to simplify this further, I can get a common denominator here by multiplying this one by Rf and this one, Rf over Rf and Ri over Ri. And what I would wind up with there will be Vn times Rf plus Ri over Rf, my common denominator, alright, is equal to V out over Rf. Alright, but the Rfs are common here, so if I multiply both sides by Rf, I wind up with V out is equal to Rf plus Ri over Ri, which can also be simplified to Rf over Ri plus 1. Alright, so we see here, all of that is multiplied by Vn, of course. Alright. So we see with this slightly different configuration, the output of this amplifier is now going to be positive instead of negative. Alright, so there's not going to be an inverting effect as there was with the inverting amplifier. Because of this configuration, we have if the input voltage is positive, the output voltage will be positive. Now the only drawback with this is that the gain, or the multiplicative factor, is always going to have to be greater than 1 here. Because of this plus 1 term here, it's going to depend upon the relationship between the feedback resistor and the input resistor. But the magnitude is always going to be some value greater than 1. So we cannot get a reduction in the input using the non-inverting input like we can the inverting input. Now, if we were to plot the behavior of this, again, we are limited by the supply rails, or the supply voltages. So if we supply a VSS plus and a VSS minus, those are the voltages that we're providing to power the op-amp. And we look at what the behavior of this circuit is going to be. It's going to be something with a slope slightly greater, at least slightly greater than 1, could be much greater than 1. And then when it reaches either the high side rail, when we have a positive input, when we have a positive Vn, our V out will be positive. And same thing, when our Vn is negative, our output will be negative until we reach the high side supply rail or the low side supply rail. In that case, if we increase the voltage input further, we are not going to get any further increase in the output, or if we decrease it more in the more negative direction, we're not going to get any more amplification or decrease in the signal output on that side. Alright, so that's how the non-inverting op-amp amplifier works.